Okay. Hello, my fellow data science enjoyers. This is the thrust two for Learn to Race, which is mainly focused on temporal learning. And this is the agenda for today. First, we'll be going over the vision of this thrust. So in Learn to Race, what you have is you have a front camera, which has a view like this. And based on that, you have to do steering and acceleration. The last year, what they did, what was the pipeline was like, you have the image, it's fed into a visual encoder, such as a VAE, and then the agent, something like an SAC, takes the actions, and you actually have those controls in the environment. This action is taken only based on what is currently seen by the camera. But in real world, we use a combination of planning, memory, and intent to drive. Some previous work that tackles this is, for example, let's say you have a model that takes in all the frames at once to encode your video. Second way is to learn the agent's dynamics with something like model-based RL. So you learn like state action transitions. Some case where these are some like main cases where this would fail, and these are like very prevalent. One is like you're making a decision near a turn, so you need to slow down earlier, go in the opposite direction. And if you see that you're going to crash, you need to slow down now and keep slowing down. The solution to this we propose is temporal learning. Now, what temporal learning is that we want to learn to make decisions not just based on the current state, but with some temporal context in mind. We need an encoder that can do two things. One is to encode motion, and second is to pass information to the next frame before encoding the next frame. Two hypotheses, these are, first one is using a temporal encoder will improve the agent's decision-making capabilities, make it just have a better context and motion understanding. Second is having a recurrent architecture will enable like faster and accurate encoding, basically, to enhance speed and safety. Moving on to requirements, we have two main uses of this system. One is researchers, and second is autonomous driving companies. Researchers would want to work on and evaluate better algorithms, and driving companies would want to test their systems in edge cases. Thank you, Dali. And for system functionality, we want to encode the visual information from this camera sensor, provide a robust encoding to the agent, then use this agent to control steering and acceleration for the car. At the end, we want to evaluate the performance of both the encoder and the agent while they're training. Some non-functional requirements, in brief, are efficiency. So it needs to process everything in real time. Performance, meaning the car should be as fast as possible. Portability, meaning we want the encoder that is easy to use with the rest of the code without damaging the modularity of the code. Reliability is we need to have the least number of crashes or infractions as possible. Resource requirements are we need compute. For us, we have the Phoebe cluster provided to us, which includes a lot of GPUs, which are either 2080 Ti's or A100s. And also, differently from last year, we need a data set to pre-train the visual encoder. This data set would be collected from the arrival simulator for different tracks. And instead of images, we need continuous videos. Now, for the design of the system, this is the same graphs you have seen earlier. And the main thing we want to focus on is the red box, which is the temporal context model. To zoom into this and to understand it better, we have an observation, which is OBS, which is coming in, basically the feed of the camera that is getting encoded by either the vision encoder or the temporal context model that is converted into a state encoding, which is, let's say, a 32 length vector or a 256 length vector. Then that is used by the agent to make actions, which is steering and acceleration, which is then again used by the environment to take that action. For design considerations, the first design consideration we had to do was how do you pre-train these models in the best way possible? So we want to pre-train this in a way so that you can pass an encoding to the agent at the end of the day. And Some of the previous work shows that learning actually predictive information helps the RL agent in like the best way possible. And for us, this means two things. One, we can learn to predict the next action given the previous frames. So have an encoder that learns next actions, or predict the next frame given the previous frames. And both of these things forces the encoder to encode motion to be able to predict the next frame. For example, we stick with approach number two, um, because that is the most easy for us. That was the most easy for us going forward. So the task is like this. You have a frame coming in, which is encoded. Then the encoding is again used as that is also encoded and like encoding two for frame two. So you have this flow, which is like something you can recognize as a recurrent flow. So at the end of the day, the frame four's encoding will contain information from not just that frame, but one, two, three as well. And then you'll have a decoder that will predict the next frame. So this is easily very similar to a convolutional architecture, wherein the encoder in the frame encoder is a convolution network, wherein you're encoding it to, let's say, a vector of 32 numbers. And then you have an LSTM that passes on this encoding to the next steps. At the end, you'll have a bunch of con transpose layers to use that encoding and to actually create that frame, generate that frame. But the main reason we use a conval STM is because at inference time, you only need the previous encoding, which is already stored. You need the current frame, you encode that, and you pass that to the agent. Unlike transformers, for which we would need to encode all the frames at runtime, conval STM gives us an efficient way to run this model, which is very important for learn to race. Now, the pre-trained data set has to be designed in a way so that, again, it's a video data set. And we wanted to learn how like a good agent behaves. So we want to use a variety of experts that the encoder can learn from to generalize to, let's say, a bad agent would be like it's crashing often. So it also sees these crashing states. A really good agent is it's very fast. It's not crashing at all. So it also sees that. So you're using a variety of experts. So we pick experts that range from like novice learners to experts. What we want ideally is a number of videos from the front camera, and each video will be of this size: length, which is the number of frames, width, height, and channels. Channels are usually three. And we can, at the end of the day, to pre-train this encoder, we want to sample continuous videos of length k, which can be decided later on for these videos. For the test design, we have two things: encoder and the agent. For the encoder, you can use various metrics such as, again, the reconstruction loss, which we stick with MSE for now, standard deviation, which we'll dive into a little later on, and latency as well. For agent, we obviously have evaluation distance, evaluation time, and evaluation speed. Some risks that could occur if for this model is that having a very high latency can mean the agent is too late to make a decision, and it is crashing before even encoding the environment state. Second is low performance. So the car or the agent is just slow and it crashes often and fails to learn what it's supposed to learn, which is not the point of learn to race. Third is a bad encoding. So if the encoder we're learning is just not that great, whatever the RL policy will get as an input is not going to be meaningful for it to learn learn a policy over. These are the tools and dependencies. For Phoebe cluster, we use Docker and Kubernetes. Then we use PyTorch, NumPy, OpenCV. Arrival is a simulator, and we use other libraries such as OpenAI Gym and stuff. For logging, we use weights and biases. So to recap, these are the design choices we made. So we use the next frame prediction task as pre-training objective. For now, we decide the context length to be as 10 to do all of these experiments. Then we want to use the conval STM architecture for efficient inference. We use a combination of experts for dataset collection. And the fourth is we want to collect data set that is videos of the car and the front camera feed. This was going forward, this is the plan. So first, the goals mainly were have a pre-train a really good encoder, use this encoder to train an agent, and then at the end, just evaluate the performance of the agent. The plan was changed as we went forward. For example, the implementation of negative log likelihood was skipped because our uh, original task of next-gen prediction performed well. So that was skipped, and we're still the joint training and end training is still in progress. But rest of the all the rest of the milestones were pretty much on time. Moving forward to the experiments and results. First, we collect the data set. So in spring, we collected like a 10 gigabyte data set with just two experts. Both were pretty novice. So in fall, we recollected this data set of 290 GBs with the following experts. Now, what we mean by avoiding concept drift is that when the agent sees a really good, let's say, condition when it's on the track, it should not be able to not understand what's happening. So we wanted to encode all kinds of states possible. So these range from a novice to winner, which is the expert. So first was a random agent, second was a pre-trained VA and soft actor critic, third was pre-trained VA and safe soft actor critic, which is much safer. And the fourth one is the Roborius challenge winner, which was like a really good model, which was around 150 mph. So we use that as also an expert. At the end of the day, we get around 268,000 samples of videos, which are all of around 10 frames. And going forward, we only use a 20% sample of this to conduct all the initial experiments. First of all, to just see what kind of data we're dealing with, this is the random agent. You can see it's just random decision. It's fast, but it's random. Next up, we have the VA in SEC, which is the last year's model, which is, again, these are randomly picked examples, but it's kind of learning. Third one would be SafeSat, which should be much safer in its actions. So it's avoiding the boundary like at most of the times. And the winner should be like really good, which is what we see. It's a really fast agent. And so, first of all, to recap from spring semester, the baseline that we had trained did not perform well. So we just tried adding a layer to the encoder and decoder to see what happens, and it didn't really work out well. What we got was a very spiky training loss. Again, this was in the pre-training stage, and the reconstructions were pretty much meaningless. So we initially we tried out a bunch of models, but the fix was to just add a ReLU layer at the end because the reconstructions were having negative values. Again, a bunch of models we tried because that was the main intuition that maybe the model is just not strong enough to reconstruct. And when we train these models, even with ReLU, at the end we see very spiky losses in training curves, nothing smooth. So it's not necessarily learning as we want it to. What we observe is when we try to reconstruct from these agents, from these encoders, is it's always giving out the same image no matter what you give it as the previous 9 frames. So it's always an image of the car in the middle of the track where like the boundaries are equal. So this is called mode collapse. So it's learning to predict only one type of image. Turns out this pre-trained task of next-gen prediction, specifically for learn to race, is very sensitive to hyperparameters. So a batch size of 32 and a learning rate of 0.0001 is very crucial. If you increase or decrease it slightly, you will get models that suffer from mode collapse. So again, one thing we did was to figure out mode collapse during training. We plotted the standard deviation of the reconstructions. So to understand it, wait, I'll come back to the slide, but the ground truth on the left is like you'll have a standard deviation of around 0.1 to 0.15 most of the time. And the one on the right is our models. But yeah, so the models we have are these. The base model, which is Cornell STM. So it's very similar to the VA, but we add 3 LSTMs in the middle. Then we have a base 256. So for this, the LSTM has 256 hidden dimension, and the base residual is basically the same base model with residual layers added. Base 256 residual, which is the best model we have, has both the hidden dimension 256 and residual layers. There's another deeper model which has just extra layers. Now, when we pre-train these models, what we observe is that so one model you can't see on this graph is called the deeper, which is almost always at 0 on the prediction standard deviation. So it's suffering from more collapse. And we see that all of the other models, the best performing model we have is called base 256 residual, which is again the largest model we have. So that gives us the best reconstructions or like the best standard deviation for now. So we use that model to actually reconstruct the images given the previous frames. And we see that we have some really good reconstructions. At least they're not at all close to more collapse. One thing to note here is that we don't necessarily want the highest fidelity reconstructions, as long as when you use this pre-trained encoder with the agent, you're performing well enough. And also, like, it's a really small, all of these are still very small models to expect great reconstructions from. The best performing model was base 256 residual. Now, when we use these encoders as pre-trained encoders and train the agent, we see that the baseline which we had again initially was SACVAE. Our model performs much better. So it's faster, it stays on the track longer, it is successfully avoiding a lot of boundaries. And one thing that's maybe not exactly clear from this video is that the phenomenon that we were expecting, so that if a right turn is coming up, you go slightly to the left and then you take a right. That's also present in a lot of videos. Maybe not so clear in this, but it performs generally better, at least in terms of this video. Then we go on to the actual metrics, and we see that the distance that's covered by the new agent, or the new model agent, is much better. So it's like at least twice as more. And the evaluation time, so evaluation time is the time it's staying on the track, and the distance is covering on the track when it's being evaluated. And we see that the performance is better across the board. The next thing that actually we went forward to do was, why do we really see these performance increases? So there's a bunch of variables at play here. Was it the newly collected data set, which is again a used data set? Was it just the pre-training task of next frame prediction? Was it the convolutional schema architecture? Or was it just the addition of, let's say, extra parameters, which were the residual or 256 hidden dimensions? To evaluate this, we take last year's VA model and train on the same data set. We use the VA with a 256 dimension, hidden dimension, convolutional with all of these combinations to figure out what's really helping us. The results show us that the VA it performs like poorly when it comes to reconstructions. So it's not just that the everything else is helping. What do you say? The task or the data set is enough. The VA does not really generalize well. So, and again, the models that you see on the right are the ones we saw previously. Again, base 256 residual performs the best in terms of reconstructions and standard deviation. And again, it should be as close to the ground truth, which is on the left, as possible. So what we learn is that VA does not perform well in reconstructions, and this increase is not marginal on the largest model. So again, going back, it's not like they're almost overlapping, and we can just use a smaller model to get for the Asian. So it's not just marginal, and a setting of pre-training task as well as the convolutional is important here, and we cannot easily just replace this largest model. That is, we both need residual layers and a hidden dimension of 256. Now, this is an experiment that's still going on, which is, what if instead of the 20% sample, you train on the whole data set? And we're kind of seeing promising results. So the reconstructions, at least standard deviation, are better, and the evaluation distance is getting better, but not sure how it will perform in the future. Also, we're getting better speeds. Some limitations that we see for this model is that it takes a really long time to encode as compared to the VA. So In the same 150 hours time, it is only doing 1/4 of the training number of steps. So it's taking four times as long to encode. But yeah, to conclude, this task of next frame prediction is a great signal for our encoder, and the combination of Cornwell STM shows promising results. Again, the data set was also pretty helpful. Going forward, we want to compare the results of this model with a safe SAC baseline, and we want to also experiment with joint and end-to-end training, so that while the agent is being trained, we also again train the encoder. Then we want to standardize the experiments to not just L2R, but other environments and analyze failure cases. Yep. And to reflection, I feel much more confident about tackling large code bases at this point, and also a lot of understanding about how encoders and our relations have their interplay. And the main thing again was the challenge was fast iterations, as said by the previous thrust, which is like you have 4 to 5 days for training an agent, so you don't really know what to do. And yeah, just that mostly. And this was changed about the negative log likelihood loss implementation, as well as just push the joint entity into the end. Yeah, thank you.
Great. So can you go back to slide 44? Okay. You went through this really quickly. And I guess what I'm wondering is, what was the motivation for each of those experimental conditions?
So basically the base model, which is the first one, did not perform as well as we expected it to. So we added, so we tried to just make it deeper or like larger.
Things that you thought might make it better.
Yeah. So I did.
So other projects using Condell SDM considered similar kinds of enhancements. So
the other part that have used Cornwell STMs don't necessarily like function the same way. So like there was one paper which again feeds all the information to the Cornwell STM and then uses those encodings. So not very similar work.
So how confident are you in how well you've explored the space of configurations with Condell SDM? Is this just scratching the surface, or do you think this is really all that's worth looking at?
I think the main thing I would say is like the task or like the retraining objective is the key takeaway here. And maybe we can do some hyperparameter tuning with the models like depth, whatever. But yeah, that's like an additional experiment we can do. Yeah.
So I think you motivated pretty well the idea that humans remember, and that a human never makes a decision without being in a context.
Yeah.
And I guess one could imagine that that would be a weakness of an agent that just learns based on exactly where it is right now and not where it was, a few seconds ago.
Yeah.
And that something like this could help, move a policy that's being trained away from mindless oscillation and so forth. But was there a real intuition by looking at specific error cases? Oh, if I had only, had 5 frames, before this encoded, this would get better. So I guess what I'm asking is, it's an intuitive idea, but did you just set out to implement this and see whether it worked, or were there particular behaviors that you observed in the baseline and said, that's not going to get better unless we're, remembering the last 5 frames?
One thing, I mean, I didn't show it here, but like with the VAE model, at least, if let's say the agent has high speed at some point, so very high acceleration, it doesn't slow down because it's like in a state where it can't go back. So it keeps on going, it just crashes. So one thing there where like context would help is like in this moment itself, you see that you're going to crash and you encode that and then like you slow it down. But yeah, I don't think I showed the specific examples.
So it's kind of like giving you a preview.
Yeah.
Of if you're gonna die in the next second. So
that's the expectation.
By the way, allow that to augment what you're doing.
Yeah.
Okay. So that's not a bad hypothesis. That's sort of some window of previous context, and then using that to predict is basically giving a little prediction of what might
Yeah.
happen in the future, that the system can use to slow down.
Well, one
So
clarification. Sorry.
we don't need to go into the details,
Sorry.
but this is, as you talk about this going forward, you want to make sure that that part of the story is super clear. Because we got caught up in a lot of the details there. And at the end of the day, sure, you can show a video of the system behaving better, but you have to be able to say what real behaviors are different that aren't there anymore. And you just started to give me some hints about what they are, which is, well, when you're going too fast, now you have a tendency to realize that you might crash because of the frame prediction. That's the kind of answer I'm looking for there. Let's see. So I think the question about what the experts are that you're using for the training of the encoder, super interesting, right? So I like the idea of taking a variety of agents and then running them, to get video, and then trying to use that to train the encoder. But I think it's pretty obvious that a real learner doesn't have access to those memories, right? So if I could have my dad's memories, or if I could remember hundreds of hours of my dad's driving, when I'm learning how to drive, that would be cool. And then if you kind of made this point at the end, so we have to really figure out how to jointly train the policy and the encoder. I find that to be probably the most fascinating part of this. But how complicated do you think that will be? Because you're going to have to figure out how many frames to remember and so on. Do you think it's feasible to train the encoder and the learner jointly?
I think it's possible. It's just too complicated to do it in the last 2-3 weeks. Also, one more thing, you don't have to remember a certain number of frames because
You're
of the way.
encoding a certain number of frames.
No, I'm saying because you are just passing the last as much as possible. There's no limit on how much you're remembering. So let's say something from 30 frames ago could also still be stored.
Right, but you have to design
while training,
coding that has the right properties.
I think one thing to note would be that rather than requiring, let's say, orchestrators process for in a principal way, collecting data from many different experts with very different sort of properties and configurations and behaviors, can actually regard different instances of the learner throughout this training progress as indeed experts. So you might see that during earlier phases of training, that might be more akin even to your random expert. Whereas during later stages, it might be more akin to sort of a more mature, more effective, more performant agent this way. And actually, if we're to sort of retain and have some way of sort of, I guess, differentiating between these different learning regimes, I actually might be able to utilize off the shelf some of the tooling that we have, for example, like offline RL. But actually already doesn't assume that the training data comes from a magically great expert, but actually could come from experts that will generate noisy data from that. So this could be one way of actually not just getting to the policy, but actually even learning an effective encoder by basically defining a offline RL training objective based on all of this data that you do have and you're able to collect, which I appreciate. So that would be like one interesting extension in addition to genetic training. Yeah, I'm certainly I'd love to see as well. I was curious actually about I think slide 17.
17.
With regard to that's correct on your choice of tasks that you might want to consider. During your presentation, I think you kind of glossed over the notion of utilizing the actions as well.
Yeah.
I'm just curious, what are your comments there? Why would you or would you not want to also include encoding and predicting actions alongside the training?
So this is again, I think, similar to the video pre-training paper, which predicts the actions given the frames. I think for now I just kept that, like, so I was planning to implement it before because this was not performing well, but because this did, I went on deeper into this instead of also trying out like
Okay, so
that
that's just
experiment.
this timing.
So that's what
Yeah,
you meant
yeah,
by east. Okay.
yeah.
I think this is actually super important for this more general case of joint learning because you really want to have something that can play around and like try different actions. And you know, the way humans learn how to drive a new car, like when you give a brand new model to some expert driver, they take it around the track slowly and then more quickly, and then they figure out where it starts to drift and so on, and they come back saying, wow, very good job, you know. But they do it essentially by understanding where they have to modulate actions, you know,
Yeah.
versus the feel of the car.
So I had a couple of questions. Can you go to your distance over time graph? Um, why you didn't work successfully?
I did not, I could not like integrate it in time. Sorry. Also the safe sack. So I'll include both that and safe sack in the report, but I could not finish it in time.
The other thing that I kind of go back to this joint training part, there have been so the kind of dominant is Google bigger better faster word, where they combine a supervised loss and or loss into itself. I think that so I want to ask you, do you think there's like an interesting kind of correlation between so there's this interesting correlation between continual learning and reinforcement learning, right? Because in a lot of ways, reinforcement learning is continual learning, but we just focus on this change as the model changes the policies, as opposed to looking at images. If you were doing this joint training, how much would you borrow from continual learning, or do you think that it's like you would want to have the same objective as you move throughout?
I'm not really sure how which objective would be useful. So the one thing they use VBF is just like, I think, some sort of data augmentation type loss. So no matter how much you augment it, it has to be the same. But I'm not really sure.
I guess way of rephrasing the question would be, do you think the fundamental learning to risk task changes over time? I guess conditioned on the maturity and experience of the learner, or do you
Yeah.
think the task remains the same?
And specifically the visions.
Vision. I think one thing we could think about, like one way you could think is like, no matter what uh environment you're in, the basic sort of like understanding the environment would be the same. So maybe initializing from this type of encoder to, let's say, another setting would be useful, but also we would need to train it again or like fine tune it for that environment maybe.
There's another answer though, which is we've seen that we were able to train policies that stick to being safe, and then they don't take risks, and then they're disappointing because they never learn how to go fast. If you literally do become more exploratory, I'm not sure your answer is holds water, because if I am learning how to go fast and I finally get to the point where I'm going fast and I'm turning and then I apply the brake because I'm in a non-safe state, and I'm going to experience drift for the first time. Vision data is not going to be the same when you're drifting.
Yeah.
Okay. Because the what you see as motion is not going to be completely correlated with the forward motion of the car or the forward attitude of the car. You're going to be looking at something that's not on center. Okay? So it's important to think about that, because you could definitely, this would be something that the agent could essentially learn without even knowing what drifting is, because your encoder can actually show this very interesting variance in the frames that arise. The predicted next frame is going to be different than the predicted next frame if I do exactly the same thing, but I'm only going 20 miles an hour. So that's an interesting thing to contemplate here, because you know, this is one of my frustrations, is how do we flip between not only, you know, performing in safety mode, but during learning, I think we're kind of converging to something that's sort of more on the safety side, than the performance side. But if you could basically, so another implication of what John is saying is that overall, we may want to have a mode where you literally don't change the policy, but you basically try to change some of the actions just to generate new data, you know, for the vision encoder to see if things, you know, look differently, and then sort of flip flop. That would be joint learning between all of the parts of the project, right? So,
That'd be great.
any other questions? All right, thanks.
Thank you.